and numerical approach to Lyapunov exponents of skew-product semiflows. Proszę.
So thank you very much for the introduction and to organizers for opportunity to talk. So I'm Marek Kryspin. This presentation, the keyword of this presentation is the Lyapunov exponents and how to evaluate it. This presentation is based on joint work with Professor Jan and a couple of my colleagues, and I will mention them also later. So the agenda for today contains 3 points. I will show very basic preliminary example and what I mean by evolutionary type operators. Then I will provide a definition of random dynamical systems. Especially, we will focus on topological linear skew-product semiflows. And the last point, main one, will be about Lyapunov exponents under some additional assumptions. I mean, I will comment this later. And how can you evaluate in the non-delay and delay case? It will be understood later. Okay, so the first thing is very easy. Like, imagine you have this system of bodies, and then you can solve it. Use it the evolutionary type operator, this matrix exponential, and this is, you have this initial value, and you know the trajectory and the evolution. You can make it a little bit more difficult, but you can still solve it very easily. So nothing interesting here. Even if the coefficients will depend on t for this perturbation, and even depends on an unknown function x, well, then you cannot write explicit formula. You have semi-explicit or formula. This is a mild formulation of this problem, or integral formulation in sense of Carr-Theodori type solution. And we will focus on this matrix U. This is a fundamental matrix, or the propagator solver of the linear part, so without it. Okay. So first of all, what is known about such matrices? So this is a identity operator at the beginning of the time. So at the initial time, this is an identity matrix. So nothing special. I mean, you have to pass through the initial value. This cocycle property holds. So this is also well known. And at the end, this is a linear bounded operator. Here, those are properties, but later on, when we define a skew-product semi-dynamical system, this will be a requirement, or more or less this. But what if we have a delay? So first of all, we don't have a point as an initial value. Now we have a function on the interval, let's say -1 and 0. So we have to know much more previous evolution to be able to say what will be further. And there is no such operator, such easy operator, acting on some finite dimensional Banach space. But now we have to change our finite dimensional point of view into infinite dimensional point of view. And we can do this via this semi-group type operators. And we can say we have operators acting on infinite dimensional phase space. It can be C. It can be a little bit more interesting. I will talk also about LP later with one additional point at 0. But anyway, the most interesting part is here. So action of this dynamical system on the initial value. Here, keep in mind that the initial value is the whole blue line is this. So this is the you can end in some point t, and you will see the history, 1 unit history, and this how you can recover full information about the solution of this problem, for example. Okay. So one more generalization before Lyapunov exponents and stuff like this. So we will introduce 2 different maps, sigma and theta. And those are, I mean, think about this independently. So this is important to keep in mind this problem independently. This I will refer measurable, this will be a topological one. So what those maps theta and sigma are. So I will define sigma first. So okay, we have this problem with the sigma, and the sigma is abstract flow on topological space. We have measurable compact topological space, and this map satisfies 2 properties. First, it is identity at 0, so it respects that, and also we have this cocycle property, and we can build on that. We can cover this sigma map, and we can define topological linear skew-product semiflow, which will be an analog of semigroup, or the solver, the family of solvers of our problem. So such a skew-product semiflow is a continuous map with these properties. So we have identity at 0, cocycle property, and it is linear bounded operator. And keep in mind that those 2 structures, the underlying topological structure in the base is respected by those x's, I mean the base spaces, kind of Banach bundles, because we have, for example, cocycle property. So can I do something here? We have this. You can see it, yes. So we have this underlying topological space omega, and we have those bundles, and in different omegas. I mean, here we have this sigma flow. Here we have Banach space, and for example, here is initial value. And when you move from here to another Banach space X, and even further, so the cocycle property is you can make a one big jump. Yes, but this structure is kind of the same. So you have the same jumps over here. So the two structures are very similar. Okay. So I defined only the topological one. The measurable one is similar, just swap continuity to measurability, topological spaces into measurable spaces, and you will end up with the definition of measurable skew-product semiflows. So will even such problems give rise to skew-product semiflows, topological or measurable? And the answer is yes. It was done. This is theorem without. I mean, it is not clear who did this first, but for topological, it was done many years ago, and I mean, in 2018, it was done by Mierczyński, Novo, and Obaya for measurable skew-product semiflow. And we improve this for p equal 1 and for c. Kind of L infinity can be treated as c because our problem has this property of regularization. So after time 1, it will become continuous. So, but anyway, those are new, and we have this structure provided by the equation, by the interval. Okay. So, what can we say about it? I mean, we have a dynamical system. Can we evaluate something interesting? And Lyapunov exponent is quite interesting from many reasons. I mean, stability and a lot of. And upper Lyapunov exponent is the biggest one. And here it is defined through the point. So we have an orbit through point x. And this is the limit, upper limit of this quotient. And sometimes we will also investigate the biggest Lyapunov exponent without x here, but then the norm will be an operator norm. So it will capture the global intuition of this exponential growth rate, because this is what Lyapunov exponent is. Okay, but Lyapunov exponent is interesting, but how this is connected with separation and continuous separation or exponential separation. And here I will provide only intuition, because full definition is a little bit too complicated, and I mean there are a lot of technicalities in it. So I will just skip it and just give you a flavor of the definition. I mean the most important part is that phase space can be split. I mean, if you have continuous separation, phase space, this infinite dimensional Banach space, can be decomposed into two parts, linearly independent direct sum, E and F. And E is space one-dimensional invariant space, invariant under the action of the semiflow, generated by vector v omega. Of course, omega is fixed. Those equations are not stochastic equations. Those are random equations. Omega is fixed, and we kind of have trajectories everywhere. So the whole equation is deterministic. But anyway, the most important part is that this space is one-dimensional. It is generated by some unit vector, and we more or less can say something about this unit vector numerically also. So this is good. So it's not pure theoretical. Okay, but why this is important, this one-dimensional invariant space? Because in this space, you can find the biggest Lyapunov exponent. So this is the generator. Every other element of this space is just multiplied by some constant. So you can evaluate the Lyapunov exponents only on this generator. And this will be the biggest Lyapunov exponent. And everywhere else, that's the third property, Lyapunov exponent will be at least smaller. So this is, you can restrict your semiflow to the second. So if your initial value don't have the component of space E, so it will only have this component from F, then its Lyapunov exponent will be at least epsilon smaller than Lyapunov exponents from this one-dimensional invariant subbundle. And another very natural question: do we have such a splitting?
Sorry, could you move this up table, because the number of slides is not seen.
Okay. So, very natural question. Another one. Do we have splitting in some natural situations, like for initial values from C or L2 with additional point or LP, and it was done by Smith for topological one, for topological case, and recently by us, I mean Mierczyński, Nowo, and Obaya, myself, for continuous functions and LP, but under only measurability. Okay, so at the yes, now we can calculate something because we have splitting. We know one subspace, one-dimensional subspace, will have this very interesting upper Lyapunov exponent. Now, can we find this upper Lyapunov exponent? So I will provide results concerning the formulas, numerically approachable formulas, to calculate one. Okay, so what is the situation? Let's say we have a torus. So this is our. This will be only. This part will be only for the topological because measurable part is in progress. So we don't know how. I mean, we have some ideas how to do this for measurable semiflows, but for topological, it was done. Let's say we have a topological flow on a torus given by this Kronecker flow. This flow is very nice. It is uniquely ergodic. It will be more or less everywhere in the space the same amount of time. It will be important later. And we will investigate only this situation without the delay. Delay will be provided later also. Let's say assume as much as you want to obtain, of course, uniqueness, to obtain skew product semiflow, to obtain continuous separation. So you have this. And it may look like a hand waving, but we have, for example, very precise conditions. Under those conditions, it is not assumptions anymore. Like we have this condition; those are very technical yet natural from application point of view. I mean, this is it can be done. It is not pure theory. And because we have this splitting, we have this unit vector, this generator of this space. And if you will act by this skew product semiflow, it will be just the multiplication of this vector because this is a one-dimensional set. Okay, and upper Lyapunov exponent in this situation can be evaluated using those two formulas. And I will prove the first one because the proof is very nice and a little bit tricky. And yes, also I should mention in Calzada, Obaya, and Sam's work, it was done for more general topological spaces than torus, but I want to show very concrete results with concrete flow, and I want to calculate something. And mi is the Haar measure. And Haar measure in torus is scaled Lebesgue measure. You can ask, but what is Lebesgue measure on the torus? But the torus is a square which is glue. So this is a kind of a Lebesgue measure on square, which is weirdly glue. Okay. So the sketch of the proof. First of all, I mean, I will prove the first one. So Lyapunov exponent is equal to this. We start from the Birkhoff ergodic theorem for continuous functions. So we don't have this measurable part almost everywhere. This is pointoids. And the averaging over time is the averaging over space of this very weirdly looking function, but it will be clear why this function was used later. And okay, keep this in mind. The second part is we can rewrite quotient from the definition of Lyapunov exponent this way. So this is the first step is super easy, and the second step is also easy. This is a formula from calculus 1. Okay, and we are using that this vector generating vector is a unit vector, so we don't have here minus some constant. But this is okay. We have those two facts. Also, we can see that the square norm of this is just the square norm of this multiplier, what I defined previously. And the derivative of this can be explicitly evaluated using facts. For example, the square norm can be rewritten as a dot product. The derivative of the dot product you can evaluate it using Leibniz rule. So you can look at the elements of the dot product. You can derivative them, and you know what the derivative of them is because you know what is the derivative of that. So this is the derivative because because you know what your equation was, and so you can explicitly show this. And now if you divide both sides by c squared is this, you will obtain this. And now you can go back. So you know this is equal to this. When you go back, you can rewrite this as this, and you are done. Because if you put if t goes to infinity, then this will be a definition of upper Lyapunov exponent. I mean, you can say in the definition of upper Lyapunov exponent there was a upper limit. Yes, but by the definition of exponential separation, you know you are in the one-dimensional bundle with this biggest Lyapunov exponent. So you can use a limit here, and this will be this, and we already know. I mean, so the limit of this is the limit of this, but this is Lyapunov exponent in the left-hand side, and this is something that can be computed. Okay, and last theorem, also by Calzada, Obaya, and Sons. This is a generalization for delay case. So you have this topological skew-product semiflows generated by this delay equation, and you can evaluate Lyapunov exponent using one of two formulas. And at the end, I would like to show some references. So, of course, Smith, this recent preprint about measurable part. Measurable part is without this Lyapunov exponent. I hope because we are working. How can you evaluate this Lyapunov exponent in measurable case? And excellent work by Konrad and Sons. They provide the formula for topological case in great generalization. So thank you very much for your time and attention.
Thank you.